Hi students, I welcome you all for control system lectures. Today's class we are going to discuss Nyquist stability criteria. As we discussed earlier, Nyquist stability criteria or Nyquist plot is an extension of polar plot. So in polar plot what we were doing is we were actually drawing from omega equal to 0 to omega equal to infinity, right? Uh, for example, if you consider a certain plot like this, where omega equal to 0 to omega equal to infinity, we would be getting with certain magnitude and phase, we got some plot here in s plane j omega axis, right? So if you are extending this from minus infinity to infinity, that means omega should be extended from minus infinity to infinity, then the plot which we get is nothing but Nyquist plot. So it is nothing but a replica or mirror image. If you are drawing a polar plot and extending a mirror image of it, then that plot we can tell it as a Nyquist plot in a simple way. So to go into more details, let us consider open loop transfer function g of s, which was given as k into n of s by d of s, where open loop zeros are numerator part and denominator is given as open loop roots. Our roots are poles, right? Both are roots, and the numerator will be given as zeros and denominator will be given as poles, right? From that open loop transfer function we know how to get closed loop transfer function, that is by g of s by 1 plus g of s into h of s. For unity feedback transfer function, h of s will be 1, and therefore if you write g of s by 1 plus g of s, you will be getting closed loop transfer function is given in equation 2 here, right? So next thing is writing a characteristic equation for closed loop transfer function. If you write a characteristic equation is nothing but the denominator function of the transfer function to 0. If you equate 1 plus g of s to 0, then what you get here is 1 plus k into n of s by d of s. So here just substitute g of s from the open loop transfer function, which directly if you solve you will get d of s plus k into n of s divided by d of s. Just make an observation here. If you observe here, the numerator of characteristic equation is d of s plus k into n of s. That is nothing but the denominator of closed loop transfer function, right? Similarly, if you observe the denominator of characteristic equation, that is d of s, is nothing but denominator of open loop transfer function d of s. It's one and the same. So by observing all these three equations, what we can conclude is poles of characteristic equation, the numerator part is denominator part. Poles are nothing but the denominator part. So denominator of characteristic equation is poles of open loop transfer function, and zeros of characteristic equation is poles of closed loop transfer function, right? As we mentioned, Nyquist plot is an extension of a polar plot in a way that if you are varying frequency from minus infinity to infinity, whatever the plot you get can be represented as a Nyquist plot. So to go into more detail, let us consider a transfer function, simple pole. And before going to the example and explaining, I want to let you know that here in Nyquist plot, we will be considering an extra plane. The plane is represented as g of s or w plane. It is actually a mapping what we do. We know what is s plane. If you have any transfer function to represent in a s plane, we know how to represent it in a s plane. And if you draw a contour is nothing but a locus around that pole or 0, okay? And whatever we are extending that contour in some other plane, that plane might be called as a g of s plane or 1 plus g of s, whatever the plane is, some x plane, right? If you are drawing a plane and extending that contour into the other plane by mapping through the magnitude and phase of the system, then that plot is represented as a contour and contour, that is nothing but the Nyquist plot. So let us consider this example. G of s is 1 by s minus 2. S minus 2 means the pole which is lying on the right half of S plane. Okay, the pole lying on the right half of S plane. Just what we will do is we will just draw a contour around that pole. Contour with certain points. So in this map, if you can see, I have pointed out 8 points starting from A. See here, A, B, C, D, E, F, G and H. 8 points, which is circulating or encircling around a pole. See, one more point I want to make here is whatever the methods we discussed till now on stability criteria are based on the pole location. The stability is based on the pole location. If it is coming to root locus, if the poles are lying on the left half of S plane, we told that the system is stable. And coming to the Nyquist, Ruth-Howard's criteria, so based on the sign change, we estimated the stability of the system. And coming to the Bode plot, frequency plot, what we are trying to do is we are trying to get phase crossover frequency and gain crossover frequency. From that we are estimating gain margin and phase margin, and through that we are estimating the stability. In this, so all those things are dependent on pole, right? So Nyquist plot, we are actually considering the zeros of open loop transfer function, right hand side zeros. That means usually we tell if the pole is lying on the right hand side, the system is unstable. So Nyquist is a scientist who proposed this, and he gave the explanation in which considering right hand side 0 also, we can able to estimate the stability of the system. Okay, so from this transfer function 1 by s minus 2, just draw a contour, point different points on the contour, and for those points we will find magnitude and phase. Right? See, if you see these points here, these are in S plane. If you are representing these points in G of S, what we have to do is just suppose A is the point which is having a distance of 1 in the real axis and J1 in the imaginary axis. Similarly, B is the distance of 2 from the real axis and J1 from the imaginary axis. Likewise, all the points we can mention in G of S. Right, here I have given in the table. You can just go through this table, and here to find the magnitude and the phase we calculated, right? How to calculate that? Root of a square plus b square from the given transfer function will get magnitude, and minus tan inverse of b by a will give us phase. So I just calculated and kept it here for this transfer function. If you observe this, here there is a sequence. Magnitude is varying from 1 by root 2 to 1, 1 by root 2 to 1, 1 by root 2 to 1, and 1 by root 2 to 1. So this is a sequence. If you draw all the points, represent all the points in plane, in some S plane, how it actually looks is, right here actually, okay, we'll draw it here. Consider this plane. See here, the first point is actually starting at minus 135. Minus 135, you know the angles, right? 0, minus 90, minus 180, minus 270. So this is nothing but minus 135. And this is nothing but 45, minus 45. And this is nothing but 45. This is 35, 35. Okay, so from the table, if you see, G of S is actually magnitude of G of S at minus 135 degrees is 1 by root 2. This is the point. Okay, and at minus 90, it is making the magnitude of 1. Similarly, at minus 45, it is making 1 by root 2. At 0, it is making 1. At 45, it is making 1 by root 2. at 90 degrees, 270 or 90, 270 it is 90, it is making 1, and again at 135 it is making 1 by root 2, and again 1. So what we need to do, we'll just join all the points starting from minus 135. So this is how it looks. So when I'm starting from A to H in the S plane, this is nothing but G of S plane. G of S plane, because we are considering G of S for all those points, and this is origin. Okay, so the first point it is at minus 135 and going towards minus 90 and minus 45 to 0, and if you observe the direction of the path which it travels, it is actually anti-clockwise. But if you observe here, what we are doing is we are going from A to B, B to C, C to D in this way. This is actually clockwise. For clockwise S plane for pole, we are getting anti-clockwise direction in G of S plane if you are considering pole. Okay, similarly if you consider 0, just check it. If you consider 0, what happens? So I just drawn here before, and it's actually same. See, if you are substituting G of S for 0 is S equal to J omega, and you just substitute 1 plus J1 in S. Okay, what you get is the numerator part in G of S. So same table, the numerator will be shifted here. Okay, similarly the magnitude you will get it as numerator term. Similarly in G of S also, angle also, if it is a denominator you will get minus, if it is a numerator 135 as a positive angle. Okay, so this is how the path looks, and here I just mentioned how it actually goes. See, it the first point is 135 degrees and it is giving a root 2, and it is going to 90, then to 45, then to 0. And what I mean to say is, if you are using 0, G of S is equal to S minus 2, the direction of the contour, the path which it travels, is actually clockwise direction, and it will end up at 135 degrees, right? So if you are considering poles, if you are considering a pole in S plane, G of S plane and G of S plane, the path will be in anti-clockwise direction. If you are considering 0 in S plane, and G of S plane will be clockwise direction itself, right? Clockwise direction itself, and it is actually following the path about the origin. Okay, this is important point. The whatever the contour or the plot, it is actually rotating. It is rotating around encircling around the origin. If we consider G of S, okay. So this actually depends on poles and zeros. Actually, in the system, if you have a number of poles and zeros, based on that only number of encirclements, this encirclement will be dependent on that. So encirclement, let encirclement be n, and number of poles are p. These are nothing but open loop right-handed poles. Okay, z is nothing but number of zeros of open loop transfer function for right hand side plane, right half plane. Okay, so in a few case studies, if you have two zeros on the right hand side of S plane, if you want to map it in G of S plane, how it actually behaves is direction will be remain same since you are using zeros. And if you are using poles, the same plot, encirclement will be 2 because n is equal to p minus z. I mentioned on the top here, n equal to p minus z. So if you are using 2 poles, n equal to 2 poles means 2 minus 0, 2 poles for 2 poles. So number of encirclements will be 2. Even if you are using 2 zeros with no poles also, n equal to minus 2. Here actually whether it is plus or minus, 2 tells number of encirclements, and direction will be given by this sign. That way you can remember. Okay, if you are having 2 poles and 2 zeros, this is actually for 1 pole and 2 zero. See, this is for one pole and two zeros, and two poles and two zeros. If you are having, this is the plot. It is not encircling because n is equal to p minus z, p is equal to 2, z equal to 2, and that will be n equal to 0. So this is how the plot looks. And let us consider the same example, right? To actually estimate the characteristic equation. See here, whatever we consider initially and showed the encirclements are with respect to g of s. See, when we consider 1 by s minus 2, we are getting this plot with respect to 1 g of s plane. If you are considering 1 plus g of s plane, what happens? We'll just check it. One plus g of s. Okay, this is nothing but the characteristic equation, right? So for the given transfer function, open loop transfer function 1 by s minus 2, if you are writing a closed loop transfer function, it will be this way. And as I mentioned earlier, the poles and zeros, the poles of characteristic equation is nothing but open loop pole. See, poles of characteristic equation is nothing but open loop pole, open loop transfer function, open loop transfer function, pole. This numerator is nothing but 0. Zeros of characteristic equation is nothing but poles of closed loop transfer function. Okay, this is actually, sorry, this is the characteristic equation. This is actually closed loop transfer function. Okay, remember those points which I gave before. And this is nothing but the characteristic equation for the given transfer function. So if you substitute s equal to j omega, it will come j omega minus 1 by j omega minus 2. See, the process is as same as the polar plot which we consider. Initially consider s equal to j omega, substitute omega values from 0 to infinity. Here the point is we are actually considering from minus infinity to infinity. And what we can do is you can directly substitute from 0 to infinity and write a mirror image. And if the plot, that mirror image, that whole plot, if it is encircling, where it is encircling is a point. If you are considering characteristic equation, what we will be getting is 1 plus g of s. If you are considering characteristic equation, we will be getting 1 plus g of s. So for this example, for 1 plus g of s, for omega equal to 0, we will get 1 by 2, and omega equal to 0, phase angle will be 0. So that means the plot will start at 0.5 and ends at 1 for infinity. Okay, when omega is equal to infinity, 1 plus g of j omega will be 1. This is how you will get only half semicircle here. You will get only this part. I just drawn the mirror image also. Okay, this is how the plot looks for 1 plus g of s. See, if you observe the g of s which we drawn before, how it actually looks is this. G of s. G of s is let me check. Okay, this is actually 1 plus g of s plane. If you draw the same thing for g of s, for initial point and final point, omega equal to 0 to infinity, and omega equal to 0, it will start at 0.2 and it will end at 0, by making angle of minus 180 and minus 90 at infinity. So this is g of s plane. It's the same problem. I am just changing the angle actually. I am changing the plane. This is g of s plane. That is 1 plus g of s plane, which I showed before. See, this is 1 plus g of s plane. This is g of s plane. What is the difference you can observe here? When it is shifted from g of s to minus, or 1 plus g of s to g of s, the encirclement also shifted with the same magnitude. It is minus 1. See, for g of s plane we got initial point as 0.5 and final point is 1. This is just a shift of the plot. Okay, so this is how the plot looks. Suppose if you have a transfer function, g of s is equal to 10 by s minus 2. For this also, if you are considering open loop, this is open loop transfer function. Consider this as open loop transfer function. Okay. For this open loop transfer function, if you are drawing a closed loop expression, if you draw a closed loop expression, what is the closed loop expression? It is nothing but g of s by 1 plus g of s, 1 plus g of s. This is nothing but the closed loop equation. And if you substitute g of s here, the denominator factor is nothing but the characteristic equation. So characteristic equation is nothing but s plus 8 divided by s minus 2. Okay. So equate it to 0, so that the pole what you get here is s minus 8. So by just adding a k value of 10 to that open loop transfer function, you are getting unstable pole to the stable pole. The pole is stable pole, right? So if I represent this in S plane, if I represent the same thing in S plane, how it looks? So pole will be here. Okay, this is for this particular 1 plus g of s, 1 plus g of s. Okay, so what I am telling is we have to consider the contour on right half of S plane. You have to consider only the contour for right half of S plane, and for this, if you draw a Nyquist, it will be this way, 1 plus g of S plane. Okay, so we'll just consider the same thing, 1 plus g of s characteristic equation, and substitute s equal to j omega, s equal to j omega, let it be this 1. Okay, in 1, what you will get? 1 plus g of j omega, g of j omega, it will be at omega equal to 0, what you get is 4. Just substitute s equal to j omega, 2 by 8 by 2, that is nothing but 4, right? Similarly, for the same thing, 1 plus g of j omega magnitude, for omega equal to infinity, it is nothing but, if you substitute infinity here, at omega, you would get 1. Right? Similarly, if you calculate the phase of 1 plus g of j omega at omega equal to 0, you will get the tan inverse of omega by 8 minus 180 plus tan inverse of omega. So this will be minus 180 for omega equal to 0, and 1 plus g of j omega at omega equal to infinity, you would get 0. So if you draw the same thing for these parameters, if you represent 1 plus g of s in S plane, it will start at starting point is 4, right? So starting point is minus 4, it's actually minus 4, and it will end at 1 in terms of magnitude, and phase will be minus 180. See, initially at omega equal to 0, you will get 4 at minus 180 degrees, and 1 will be at 0 degrees. Okay, so when it starts and ends in this way, just we need to draw a mirror image. So this is how it looks. So this is one encirclement, 1 plus g of j omega encirclement about origin. See, if you are considering 1 plus j omega, you have to consider origin. If you are considering g of j omega, for the same thing, there will be a shift, that's it. See, same thing if you draw in g of j omega plane, there will be a shift j omega, and this is how the, see, I'm drawing with the free hands. This is how it looks actually. This will be 5, this will be 0. There will be shift from this point. There will be just a shift. So encirclement will be about -1 plus j0. Encirclement about -1 plus j0. So this is how the Nyquist plot actually looks. Okay. So we'll see the numerical problem in the next class.